You know, in machine learning, sometimes the most elegant solution is actually the simplest. So today we're going to talk about a super clever algorithm called the support vector machine, or SVM. At its heart, it has one single mission: to find the absolute best, most perfect dividing line between two different groups of data. Okay, let's just jump right in with a pretty simple question. Imagine you've got two bunches of data points, let's say black dots and white dots. Your job is to draw a line that separates them. Sounds easy enough, right? But here's the real challenge. How do you draw the single best line that does the job perfectly? I mean, look at this. We could draw all sorts of lines. Line H1, for instance, is a total failure. It cuts right through the black dots. Now, H2, it technically works, it separates them, but it's hugging the data points really tightly. That feels risky, right? A single new dot could easily end up on the wrong side. But then, look at H3. It gives both groups the most breathing room possible. It carves out the widest street right down the middle. That one? That's our winner. So this perfect dividing line actually has a name. It's called the maximum margin hyperplane. Now, hyperplane might sound complicated, but it's not. In 2 dimensions, like what we're looking at, it's just a line. Easy. If we were in 3 dimensions, it would be a flat plane. And in any dimension higher than that, we just call it a hyperplane. The whole goal of an SVM is to find this one exact hyperplane. So why are we so obsessed with making this margin, this street, as wide as possible? Well, it's pretty simple. A wider margin means our classifier is way less likely to get things wrong when it sees new data for the first time. It's more robust, it's more confident, and it's less likely to be thrown off by the specific data we use to train. So how does the algorithm actually find this perfect wide street? You'd think that every single data point has a say in where the line goes, right? But here's the magic of the SVM. It turns out it only listens to a very select few. The most important players in this entire game are the ones living right on the edge. Take a look at this. See those data points sitting right on the dotted lines, right on the edge of our margin? Yeah, those are the ones that run the whole show. These critical points are called the support vectors, and they're called that because they literally support the entire boundary, kind of like pillars holding up a bridge. Think about it. You could get rid of almost any of the other data points, and that boundary wouldn't move an inch. But if you move just one of these support vectors, the whole model could change. This is what makes SVMs so incredibly powerful and also really memory efficient. They build the entire dividing line based only on the most critical points. But, so far, we've only been looking at data that's nicely laid out, easy to separate with a straight line. The real world is rarely that clean, which brings us to one of the most brilliant and, honestly, coolest ideas in all of machine learning. I mean, what do you do when your data is all mixed up? When there's just no way you can draw a single straight line to cleanly divide the two groups? Sometimes the data is just a jumbled mess. You might even have one group of data completely surrounded by another. Yeah, good luck trying to draw a straight line through that. A simple linear classifier would just give up. But an SVM has a secret weapon. And that secret weapon has a name. It's called the kernel trick. Okay, this is where things get really, really cool. The kernel trick is all about changing your perspective. So on the left, you see our messy, impossible 2D problem. But instead of trying to solve it there, the kernel trick projects the data into a higher dimension. And suddenly, what was all tangled up in 2D becomes perfectly, easily separated by a simple plane in 3D. It's like magic. And here's the trick part. The SVM can figure out where this separating plane is using some brilliant math, without ever actually having to calculate all the new 3D coordinates. That's what makes this so incredibly efficient and powerful. Now, this whole thing didn't just pop up out of nowhere. It was a journey. The original idea for the algorithm actually started way back in 1964. But it wasn't until 1992, almost 30 years later, that the kernel trick was proposed, which is what really unlocked its power to handle complex problems. Then, a few years after that, in 1995, they introduced the soft margin version, which let the algorithm handle noisy, real-world data, making it practical for just about everything. All right, so we've got this amazing theory, super powerful stuff. But what's it actually for? Where do you see support vector machines out in the wild? The applications are honestly all over the place. We're talking about things like categorizing documents, which is a huge part of how search engines and spam filters work. They're also used for image classification, for recognizing handwritten numbers and letters, and even for some seriously complex science, like classifying proteins or sifting through massive amounts of satellite data. And they're not just used, they're really good at what they do. For instance, there's research in image classification that found SVMs get significantly higher search accuracy than older methods, and they get there fast, in just a few rounds of learning. That's a huge deal. Okay, but let's be real here. No algorithm is a silver bullet, right? Every tool has its place, and while SVMs are amazing, it's important to understand where they shine and where they don't. So on the pro side, they're fantastic when you have tons of features, what we call high-dimensional spaces. And as we saw, they're super memory efficient because they only care about those support vectors. But on the con side, you absolutely need well-labeled data to train them, which can be a real pain to get. The inner workings can also be a bit of a black box. It's not always easy to see why it made a certain decision. And at its core, it's really built to separate just two classes. Anything more than that takes some extra workarounds. When you really step back and think about it, the support vector machine is more than just a piece of code. It's this beautiful idea, a powerful reminder that sometimes the hardest problems aren't solved by brute force, but by a simple change in perspective. It teaches us that looking at a challenge from a different angle, a higher dimension, if you will, can transform an impossible puzzle into something elegantly simple. So it leaves you with a question, doesn't it? What problem in your world, if you just looked at it a little differently, might suddenly have a solution?